Welcome to this presentation. In this model, let us discuss about the aperture antennas. Aperture antennas constitute a large class of antennas which emit electromagnetic waves through an opening. Part of the structure of an aperture antenna is an aperture or opening through which electromagnetic waves flow. And an aperture antenna operating as a receiver collects waves via the aperture. The gain of an aperture antenna increases with the square of the frequency. And the main advantages of aperture antennas are its radiation is greater than two-wire transmission line and the radiation is omnidirectional. And the disadvantages are the VSWR will increase when you are using aperture antenna and it has poor radiation. And the aperture antennas can be mainly used in micro applications, surface search radar applications. Aperture antennas are based on Huygens principle. Huygens explained in a simple way the bending of light waves around an object. Every point on a wavefront may be considered as a source of secondary wavelets which speed out in the forward direction at the speed of light. The new wavefront is the tangential surface to all of these secondary wavelets. This is shown in this figure for both plane wave and spherical wave. So figure shows how a plane wave and a spherical wave can be constructed from secondary waves. The envelope of the secondary waves form the new wavefront. The secondary source concept shows that the secondary waves will spread out away from the aperture and there will be a smooth blending of the lit and shadow regions. Huygens principles evolved into the mathematical form referred to as the equivalence principle. The field equivalence principle replaces an aperture antenna with equivalent currents that produces radiation fields equivalent to those from the antenna. This diffraction effect is shown in this figure for a slit in an opaque screen with a plane wave incident on it. So in this diagram, let us say that Js is the electric current density and Ms is the magnetic current density. If a perfect electric conductor is placed along S, Js will vanish. The explanation is often given that the electric current is sorted out by the conductor. This leaves the magnetic current density Ms radiating in the presence of the electric conductor, producing the external fields. Similarly, a perfect magnetic conductor can be introduced along S to eliminate Ms, leaving only Js. So that is that you can see in this figure, right? So the fields E and H in the region Z greater than 0 in general are found by first evaluating A and finding E and H. The magnetic vector potential is found appropriate to the geometry. So A is equal to mu into e power minus j beta r by 4 pi r double integral or S js of r dash into e power j beta r dash into ds dash. So the electric field vector potential F associated with the magnetic current density is then given as F is equal to epsilon e power minus j beta r by 4 pi r double integral over S ms of r dash into e power j beta r into ds dash. So the far field pattern is given by EA is equal to minus j omega into a theta into theta vector plus a phi into phi vector. The far zone magnetic field arising from F is given as such F is equal to minus j omega into F theta into theta vector plus F into phi vector. Since the solution is in the far field and the electric field associated with the HF, and we can write this EF equation as shown in this figure, that is minus j omega eta into minus Fi into F theta into theta vector plus Fi into phi vector. The total electric field is then found by summing the contributions from each element. So E is equal to EA plus EF, that is given by minus j omega into A theta minus eta F phi into theta vector plus A phi plus N eta into F theta into phi vector. So the equivalent system of the figure A involves both the electric and magnetic current densities. Then the radiation fields for Z greater than 0 are found by one of the three equivalent systems. That is, when the Js and Ms on S, then E is equal to A plus EF. 2 Js on S, then E is equal to 2A. And 2 Ms on S, that is E is equal to 2EF. And there are many types of aperture. But most of the apertures will be rectangular in shape. It may be either circular also. For example, many horn antennas have rectangular aperture. Another example of a rectangular slot in a metallic source structure such as waveguide. So this figure shows a uniform rectangular structure with a width of Lx and breadth of Ly. The uniform rectangular aperture has an effective aperture equal to its physical aperture. Uniform illumination leads to the most use of aperture area. It is excited in an idealized fashion such that the aperture fields are confined to Lx and Ly. If the aperture fields are uniform in phase and amplitude across the physical aperture, then it is referred to as the uniform rectangular aperture. Suppose that the aperture electric field is Y polarized, then the uniform rectangular aperture electric field is aperture field EA will be given as Y into E naught, where X is less than Lx by 2 and Y is less than Ly by 2. Then the power Py is given as E naught into Lx Ly sine of beta Lx by 2 into U divided by beta Lx by 2 into U into sine of beta Ly by 2 into V by beta Ly by 2 into V. So then E theta is given as j beta into e power minus j beta r by 2 pi r into E naught Lx Ly sine phi into sine of beta into Lx by 2 into U by beta Lx by 2 into U sine of beta Ly by 2 into V divided by beta Ly by 2 into V. Whereas E phi is given as jb e power minus j beta r by 2 pi r E naught Lx Ly cos theta cos phi into sine of beta Lx by 2u into divided by beta Lx by 2 into u into sine of beta Ly by 2 into v and divided by beta Ly by 2 into v. So in the E plane phi is equal to 90. When you substitute this value, then E phi will be j beta into e power minus j beta r by 2 pi r into E naught Lx Ly sin beta L by 2 into sin theta by beta L by 2 into sin theta. So in the H plane, the E phi can be written as the same equation, but the cos term becomes 1. And the beam solid angle omega A is given by 4 by 2 pi lambda the whole square into Lx into Ly into pi square. So when you cancel out these 4 and pi square, the final beam solid angle is given by lambda squared into Lx Ly. The directivity of the rectangular aperture with uniform amplitude and phase is given by du is equal to 4 pi by omega A, which is given as 4 pi by lambda squared into Lx into Ly. And in the antenna design problem, high directivity is not only the parameter to be considered, and frequently low side lobes are also important. The side lobes can be reduced by tapering the excitation amplitude toward the edges of the light source. And this diagram shows the open-ended rectangular waveguide. One of the smallest aperture antenna is the open-ended waveguide. It requires no construction since the antenna is the open end of the waveguide. It is often used as a probe, such as the near field measurement range because of its compact size. The aperture electric field is cosine tapered in the x direction with the length Lx is equal to A and is uniform in the y direction with the length Ly is equal to B. So this diagram shows the radiation pattern of an open-ended rectangular waveguide. Thank you.